Hello folks, so in this video I'm gonna prove the Euler's reflection formula. So the formula is like this: gamma z into gamma 1 minus z is equals to pi upon sine pi z. So this is the formula that I'm gonna prove. Yeah, of course this is a very useful formula in simplification purposes, in integration also, in complex number also, mostly in integration. Okay, so first I will make you aware with the gamma function that was given by Leonhard Euler. So the gamma function definition is gamma z equals to limit n approaches infinity n to the power z into n factorial upon z into z plus 1 into z plus 2 till z plus n. So this is the basic definition of gamma function given by Euler. And so just substitute z by 1 minus z, you will get 1 minus z, you will get a limit n approaches infinity. Just put z as in the place of z, put 1 minus z, so you will get this. And now multiply these two, gamma z into gamma 1 minus z, because this is what we want to prove. So I'm going to multiply these two equations. So on the LHS we will have gamma z into gamma 1 minus z, and on the RHS I will have, multiplying this, we will get a square of n factorial and n to the power z into n to the power 1 minus z. And on the denominator you will see that this z plus 1 combined with 1 minus z, 2 plus z combined with 2 minus z, 3 plus z combined with 3 minus z will make a square minus b square formula, and this z will remain single. Yeah, now move z into this, so I am gonna write it in form of a square minus b square again. So that is I have done here, just use the identity. And I have separated the last term because last term also is not, we don't have a pair for the last term, because this n plus 1 minus z does not have a pair in this. So I have separated it out, and I have taken n from, because if you multiply these two you will get, remain with just n. So I have taken this n here. So this is n upon n plus 1 minus z, limit n approaches infinity. I have just separated this term out for simplification, obviously, because there is a pattern forming, and here this is odd one out, so I have separated it out. Again move on. So on the denominator we have this, and I am taking this n factorial square and separating it 1 square, 2 square, 3 square till n square, and giving it to the denominator. See, a pattern is forming, right? After we divide it, it will come to 1 minus z square by 1 square, 1 minus z square by 2 squares. You see the pattern, right? Okay, so this is the pattern that we have formed on this one. Okay, and also if you see here, by dividing n on numerator and denominator, it will get to 1 upon 1 plus 1 minus z upon n. N approaches infinity, this will tend to 0, so 1 upon 1 will be nothing but 1. So this limit will approach to 1, so I have taken it as 1, and I'm going to separate, I am going to solve this part, because this is approaching to 1. So this limit is 1, so approaching not, this limit is equals to 1, so that's why this is 1. I'm going to work on this because that is 1. Now if you see, I can write it as a continued product, some continued product form, pi, using pi, k equals to 1 to infinity and 1 minus z square upon k square, and yeah, this z is single, obviously. And now I'm gonna use another very useful formula. I'm not going to use it, I'm going to prove it, obviously. So, and this, I'm calling this as equation 1, and I'm going to use it later, and I'm going to derive another beautiful equation here. So this is the graph of sine. Okay, you can see the roots are integral multiples of pi: 0, pi, minus pi, 2 pi, minus 2 pi, 3 pi, minus 3 pi. You understand, right? So I'm going to write sine x equation as the product of its root. Basic equation writing like product of its root equals to the function. So this is the sine x function, and its roots are 0, minus pi, pi, 2 pi, minus 2 pi. So if you write, I hope you understand this much, that x equals to pi is the root. So I'm writing it as, if you solve this one, so it will get to x equal to minus 1 and into pi. If you equate it to 0, so it will get to x is equals to minus 1 into pi, and x equals to minus pi. And similarly, if you equate this to 0, you will get x equals to pi. So these are nothing but the roots of this equation, so I have written it like this. fine. Again, so I'm going to combine these two terms, and again 1 plus 2 x by 2 by 1 minus x by 2 pi, I'm going to combine those two and use the identity a plus b into a minus b equals to a square minus b square. So that I have done here. If you can't see it, then you can write the next terms also, you will see it. That's basic. Again, at place of x I am replacing it with pi z. In x I am writing pi z. So sine pi z is equals to, in place of x I just write pi z. So this pi will cancel out, you see, that's why I did that. So this equation will 1 minus z square by 1 square, 1 minus z square by 2 square, and so on. And now take this pi to the denominator. So this is sine pi z upon pi equals to z into, and writing this in the form of pi, continued product, k equals to 1 to infinity 1 minus z square by k square. That is that. Again, so I'm gonna reciprocate it and write it, just reciprocate both sides. So you will get pi by sine pi z equals to this thing. Now again, if you see, this thing is nothing but that equation 1 that we derived. That equation 1 is nothing but this. So I'm going to use equation 1 and equation 2 and I'm going to equate them. So I will get gamma of pi z, because this equals to this and this equals to this. So this equals to this. Simple mathematics. So this is the equation that we get, and this is what we were trying to prove, because this is the Euler's reflection formula. Yeah, you can see it here. We have proved it. Congratulations.